Applied Science 1 subject, Unit 4, and in that the first chapter, that is the interference. Already you have studied some concepts regarding the interference, like its definition, what are the different types of the interferences. Before starting this chapter, I would like to ask you one question, 2-3 questions that I would like to ask. First is regarding the anti-reflection coating. You might have heard the word anti-reflection coating, or you might have seen some glazing colors on the lenses of cameras or the spectacles, that violet color shade that you might have observed. Why is it there? That do you know? Secondly, how to find out the wavelength of a monochromatic source from the interference concept. Also, how we can find out the refractive index of the material accurately. Also, how beautiful colors are formed in soap bubbles, or you might have seen the oil film which is floating on the roads. How these beautiful colors are observed, what is the science behind it, how we can explain, how we can understand the nature of that. So that is what we have to understand from this chapter. That is why this chapter is very interesting, and also it is also very useful for the examination. First, let us discuss some objectives of this chapter. After the lecture, students will be able to understand and explain the concepts like phenomenon of interference, interference in thin films, Newton's rings formation and application, Michelson's interferometer and application, applications of interference. Let us discuss some points in the syllabus. What is the syllabus? So, interference of waves, interference due to thin films of uniform with derivation and non-uniform thickness without derivation, fringe width. Also, Newton's rings is there, applications of Newton's rings for determination of first wavelength of the incident light or radius of curvature of a plano-convex lens, and the second application of Newton's ring, that is the refractive index of a given liquid. Also, we have to study in the syllabus, it is the Michelson's interferometer, applications for determination of wavelength of a monochromatic source, refractive index or thickness of a transparent material, and lastly the engineering applications of interference, 2 applications, that is the testing of optical flatness and the non-reflective or anti-reflection coating. So this is about the syllabus. So before starting this chapter, that is the interference, let us discuss something about the light. What exactly is the light? How light is produced, or what is the nature of the light? That is what we have to understand. How light is produced? You might be knowing that. So when electron in the excited state falls from higher energy level to the lower energy level, energy is liberated in the form of photon. So in this way light is produced, that all of you know. What is the nature of the light, or means how the light is propagated? So all of you know that light is propagated in the form of electromagnetic waves. So in the figure that all of you can see here, the wave is propagating here. One is the electric disturbance and the other is the magnetic disturbance, which is perpendicular to the electric field. So both the fields, that is the electric field and the magnetic field, both are perpendicular, both are vibrating. Actually what happens here is like this. When first disturbance of the electric field is happening in the, let's say, vertical direction, because of that change in the electric field, it causes a production of the magnetic field in the perpendicular direction. So in this way, this disturbance simultaneously goes on and it proceeds in the further direction. So in this way, as you see in the figure, that in this way this electromagnetic wave propagates. What is the nature, or what exact interference? And the second is the destructive interference. So what is the constructive interference? So from this first figure that you are seeing in the slide, that you can see that is the constructive interference. It is a superposition when the two waves arrive at the point, the two waves which are having the same frequency, and also that you will see that these two waves are in the same phase. That is very, very important. Both the waves are in the same phase, and that is why resultant wave will have the amplitude which is the addition of the amplitudes of both these two waves, and hence the resultant amplitude is always greater than the individual amplitudes of the two waves, and that is why you will find that the point or that particular pattern is bright because of this constructive interference. Now in destructive interference, in the second figure that all of you can see, the two waves here when come together at the point which are out of phase, at that time there is the subtraction of the amplitudes, and the resultant amplitude will be the lower than the individual amplitudes of the two waves, and hence it is called as the destructive interference, and amplitude is lesser, and also that is why the pattern is dark, and this is called as the destructive interference. Now these are the two types of the interferences. Now the path difference condition is also very important. All of you might be knowing that this path difference for this constructive interference is equal to integral multiple of wavelength. That is, path difference is equal to n lambda, where n is equal to 0, 1, 2, 3 and so on. And path difference condition for destructive interference is path difference is equal to odd multiple of half the wavelength. So that is, path difference is equal to twice n plus 1 into lambda by 2, where n is equal to 0, 1, 2, 3, like that. You might have seen the pattern, interference pattern, because of the two slits. So in the figure you can see here Young's double slit experiment, in which you can see the interference pattern which is produced because of the two slits. Now here in this figure, all of you can see here a single source is there. From that single monochromatic source we are getting the two sources because of the two pinholes, and these two sources are now the coherent sources, and they are satisfying all the necessary conditions for the good interference pattern, and from these two sources rays will interfere on the screen, and we can observe the alternate bright and dark fringes on the screen. So that is the interference pattern that all of you can observe. Now what are the conditions for interference that are necessary for the good interference pattern? So conditions are like this. First, the two sources must be coherent, means they must be in the phase or out of phase, like that. The courses must be coherent. Secondly, the sources should be monochromatic. Third condition is that the two sources which are producing that interference pattern must be narrow, very small. They should not be very wide. And lastly, the sources should be close to each other. They should not have a long distance between them. So this is the fourth condition. So if these four conditions are satisfied, you can observe a good interference pattern on the screen. One more concept we have to understand here, that is called as the equivalent optical path. Now what is this equivalent optical path? The definition can be like this. The optical path represents the distance light travels in a vacuum in the same time it travels a distance d in the medium. A distance d traversed by light in a medium of refractive index mu has its equivalent optical path mu d. You can get the clear idea regarding this equivalent optical path from this figure. Now from this figure you can see that when light travels through a medium of refractive index mu, the distance traveled is d. If that light would have traveled the path in a vacuum or in air, it would have traveled the path mu into d in the same time. So the equivalent optical path of this distance d is mu d. So this is the concept. This can be again clarified from the second figure here. So how there is change in the propagation of light in the particular medium and in vacuum.